In this lesson, we're going to look at functions of two variables and try to understand the rates at which those functions vary. In particular, we're going to be looking at what's described as the partial derivative of a function, and we'll see how that's computed in our first example. The function we'll be looking at will be called f, and its value for numbers x and y will be given by squaring the x and then multiplying the y by 3 and then adding them together. So the value of the function f for the number x, y will equal x squared plus 3y. And we'll keep track of that number with the variable z. Here we have the computation of the value of the function f for the number x equals 2 and y equals 1. So we take 2, we square it, we take 1, multiply it by 3, and then add them together. The result is 7. Let's see how that's visualized in our mapping diagram. First, notice that we have three axes: the x-axis, the y-axis, and the z-axis. And on these axes, we have various numbers indicated as points on the axes. For the function f evaluated at 2, 1, which turned out to be 7, we want to visualize this on this mapping diagram with these three axes. So we find the number 2 on our x-axis, we find the number 1 on our y-axis, and to start with, we will draw a line segment between those two to indicate that those two numbers are the numbers that we're working with. We're going to draw arrows from the number 2 to the number 7 on our z-axis, and from the number 1 on the x-axis, we'll draw an arrow to the same point. So what we have is that the number 7 is equal to f of 2, 1, and we have that visualized in this mapping diagram. We can change the value of x and see its value change dynamically. There the values of x are being increased, and here they are being decreased. Let's return it to 2. And we can do a similar thing with the values for b. We can change them up and down. And we see the values of the function changing in the z-axis as well. So here we are at the number x is 2 and y is 1, and the value is 7 for our function. Now we can do this with many more pairs. For example, let's look at keeping the b fixed and pairing the b with other numbers from -3 to 3 on our axis. Here's what that looks like. So we have all of these dotted lines representing the pairs 2, 1, but also 3, 1, 1, 1, 0, 1, -1, 1, -2, 1, and -3. We can look at different pairs by changing the b. So here they are, paired, different pairs with 2, or different pairs with 0. There are many ways to pair the values of our x's with the values of our y's. Now I want to show you some values for these pairs of x's paired up with the number b. So here's what they look like. There's lots of arrows. So here's the arrows. Well, that's getting a little messy. Let's take out the pairs, and we see the arrows here showing us the values from the x. This is still pretty messy, so let's take out our original 2, 1 and just look at these pairs. So these are all the arrows from the x's to the z's, from the numbers -3 to 3. And if we look at this, we note that we really don't need the y-axis. So let's take out the y-axis here. Now we have z is just a function of x. Of course, it depends on b equaling 1, so we've left that b equals 1 in our picture. And all of these are now values depending on b equals 1. We can show how the values of our function vary, keeping the b fixed at 1, but letting the x vary. Let's bring it back to 2. In this visualization, what we have is z is a function just of x because we fixed the b equal to 1. Let's think about what that function is. That function, which we'll call g1, is found by taking the function f and evaluating it with any x, but with the second variable, the y, set equal to 1. So it's x squared plus 3 times 1. This function g1 is a function of one variable, and this is the mapping diagram that visualizes that function of one variable. Let's take out the sampling and see how this looks as we just vary the x again. So as we vary the x, the values of z change. Sometimes they change faster and are decreasing. Sometimes they change slower. What we want to know is, how fast is the z changing when it's just controlled by the x and the b is held fixed at 1? This information, this rate, is the rate at which g1 is changing at any particular point. That rate is kept track of with the derivative. What is the derivative of our function g1? It's just 2x, because the derivative of g1 is the derivative of x squared, that's 2x, plus the derivative of 3, which is 0. So the derivative of g1 with respect to x is 2x. So that's telling us the rate at which the function f is changing when the x is allowed to vary, but the other variable y is held fixed at 1. And that's what we call the partial derivative of the function f. It's usually denoted with a curly d and the function f, and then using the Leibniz notation, a differential notation, we use a curly dx. So the partial derivative of f with respect to x when y is 1 is equal to the derivative of g1 with respect to x, which is equal to the derivative of our original function f evaluated at x and 1 with respect to the variable x. The partial derivative of f with respect to x is the number 2x for any particular x. We summarize that and say that the partial of f with respect to x at the number 2 for x and 1 for y is the derivative of g1 with respect to x evaluated at x equals 2, which we found to be 2x. We're going to evaluate that at 2, so that's 2 times 2, that's 4. So the partial derivative of f with respect to x at the pair when x is 2 and y is 1 is the number 4. The partial derivative is a number, and that number represents the rate at which the function f is changing when x is 2 and y is 1, and the x is allowed to vary. And we see that visualized in our mapping diagram as describing the rate at which the function is changing as we move through the number 2. The concept of a partial derivative can be applied in many situations. If we want to extend our work here, the first thing to do would be to think about a different value for y. So the y could be any b. The work would be roughly the same, and the result would be that the partial derivative of f with respect to x at the point ab would just be the derivative of f treated as a function of x with the y set equal to b with respect to x, evaluated when x is a. That would give us 2a. Comparably, one could talk about the partial derivative of f with respect to y. That would allow us to fix the a and let only the second variable, y, vary, and then find the derivative of that function with respect to y and evaluate it when y was equal to b.